So, electric potential at a point, that is what we will discuss now. It is potential is denoted by V. Electric potential at a point is potential energy of unit positive charge placed at that point. That means we can write here V equal to U divided by Q. Actually, it is hard to place a unit positive charge because plus 1 coulomb charge is a huge charge. So, huge charge that in your entire life you may not have seen 1 coulomb charge if you sum up all the charges you encounter. So, another way to define is that, so suppose if test charge Q has potential energy equal to U at a point P, then the potential at P is given by V equal to U divided by Q. Obviously, limit this Q tends to 0. Okay. So, it is potential energy divided by the charge. So, we know from definition of potential energy, if you have 2 points 1 and 2, difference in potential energy U1 minus U2 equal to integration of F conservative dot dr from 1 to 2. So, if you divide it by the charge Q equal to integral from 1 to 2 F conservative or electrostatic in this case divided by Q dot dr. Now, F conservative divided by Q is nothing but the electric field. So, and this U divided by Q is V. So, V1 minus V2 is integration of E dot dr from point 1 to point 2, right. So, determining potential at a point, say this point charges Q1 and Q2. So, at this point P at a distance R1 and R2 each from the charges. So, at P potential equal to KQ1 by R1 plus KQ2 by R2. Okay. Now, what is the relation between field and potential? Say for that we can first recall from our past knowledge relation between force and potential energy. Obviously, the integral form we have seen in the last page, but that differential form, say suppose this is the x axis, now this is x and this is x plus dx. Now, there happens to be this force Fx and obviously there may be Fy and say Fz also, z perpendicular to both. Okay. But u at x minus u at x plus dx equal to only the work done due to Fx matters, Fx multiplied by dx. Therefore, Fx equal to, we will put a minus sign, u at x plus dx minus u at x divided by dx. Actually, it is u at, or we can write it again like this, minus u at, this is x plus dx yz, because see, you take a line parallel to the x axis. So, the y and z coordinates do not change. So, xyz divided by dx. So, this is nothing but differentiating u with respect to x, keeping y and z constant. So, that is actually a partial derivative. So in the same way, we find that fx equal to minus del u by del x, fy equal to minus del u by del y, fz equal to minus del u by del z. For potential, the same thing will apply for the field. The field x component is minus del v by del. It is nothing but this all three things divided by the charge q. Similarly, Ey equal to minus del v del y, Ez equal to minus del v del z. Okay, I guess you know how to find out partial derivative. Okay, say we take out a function. Suppose, for example, if v equal to a times xy plus yz, right? Now to find magnitude of the field, find the electric field at point say 1 1 1 1 1. Okay, for that Ex equal to how much? Minus del v del x, that is minus a times y. Okay, because you are differentiating with respect to x, keeping y and z constant. Similarly, Ey equal to minus del v del y, that is minus of a see x plus z, right. Now Ez equal to minus del v del z equal to minus a differentiate, that's y. Okay, so you get this as minus a, that is minus, see x y and z each are 1, so minus 2a, and this is minus a. So you can find the magnitude by root over of square of this plus square of this plus square of this. Okay, now this potential due to a spherical shell, uniformly charged spherical shell. It has radius r and charge q. Now you know the field variation, that field distance r, this is the field up to r, the field is 0. Beyond r, the shell acts like a point charge at its center. So similarly, you can find potential for outside point. Now if r greater than r, potential is equal to, then it will act like a point charge at its center. Same. Now if r is less than r, that is for points inside, so for points inside the shell, what happens inside the shell, as the potential as the field is 0, here the field is 0, therefore potential is same at all points. If the field is equal to 0, then potential is same at all points. Now potential at the surface, you know, so for this shell, so at the surface, that is r equal to capital R, potential is equal to kq by capital R. Therefore for all points inside the shell, potential is equal to kq by capital R, is constant throughout. Or you know that that field is equal to minus dv minus del v del r here in terms of the radial coordinates. R. So here as E is 0, so V is constant throughout, and obviously this constant value is this. So if you draw the graph of potential versus distance, a small r from the center of that shell, it will be like this. Here it's constant, and beyond that, so this is constant at kq by capital R, and here the equation is kq by small r. Okay. Now we'll take up a problem of concentric shells. When we learn about the Gauss's law, we'll deal with concentric shells in more details. But just to explain how potential, to calculate potential and apply the principle of superposition, just one problem. So this is a shell, radius R1 and the charge is Q1, and another a green shell. This is having radius R2 and charge Q2, and both share a common center O. Okay. Now I will choose some points and calculate potential at those points. Say I choose a point here, P1, say one more point here, P2, and a point here, P3, and say we have to mention the distance actually. So from point O, the distance of P1 is equal to say R1, and distance of P2 is equal to R2, and distance of P3 is equal to R3 from the center. Okay. Now to find potential at point P1, P2 and P3, we will start with P1. So potential at the point P1, then we will apply superposition, say violet and green, right. Now at point P1, potential due to the green shell is how much? So when you calculate potential at P1 due to the green shell, forget about this violet shell, right. So that is what superposition is. So bring in the green first. Due to the green shell, it is k q2 by r1, this plus, okay. Why kq2 by r1? Because see, due to the green shell, this point P1 is outside the shell, right. So for outside, this whole charge q2 will act like a point mass at its a point charge rather at its center. Now due to the violet shell, for the violet shell also this point P1 is outside, so kq1 by r1, right. Now let's take this potential at point P2 is due to the green first, okay. So due to the green shell P2, oh, due to the green shell, this point P2, now forget about this violet shell, this point P2 is inside the green shell. So for inside point, the potential is constant, that at the surface. So that is k q2 by capital R2 plus, due to the violet shell, purple shell, it's outside, so kq1 by R2. Next, this one, try to do it here, P3. Now due to the green shell, it is inside, So KQ2 by R2 plus with the black one. Now due to the violet shell, this is also inside. So inside the violet shell, it's KQ1 by radius of 1. This is the way to calculate potential due to concentric shells. Okay, now we'll calculate potential due to a uniformly charged solid sphere. We already know the calculation of the electric field due to this one. So this is the uniformly charged solid sphere. It has charges throughout its volume. Uniformly charged solid sphere, say charge Q and radius R. Now say consider a point P outside. For the point outside, this will keep the small r variable. So first case, capital R is greater than small r is greater than capital R. Capital R is the radius and Q is the total charge. So for that potential, simple, this whole thing will act like a point charge by R. Now next is inside points. Okay, for the inside point, say now this is R. For the inside point you have to calculate potential. Now for this, inside, this is the field. The field is rho r by 3 epsilon r, that will come to be kq by capital R cube multiplied by small r. So add a point, say this one, say point P dash. So Vp dash minus Vs, let us take a point on the surface S. I'll make one more diagram for this. So this is a solid sphere charged, and suppose this is a point P dash, this distance is R, and this is a point S on the surface. Okay, and the field is equal to, formula is kq by capital R cube multiplied by small r. So Vp dash minus Vs is equal to integration of this E dot dr from R to capital R. Now Vp dash minus, now V at surface, then also just for the outside point, it is just the limiting case when small r is equal to capital R. So it's equal to kq by capital R is equal to this kq by R cube integral of r dr, r square by 2 and minus r square. So for inside point, Vp dash is equal to, if you add up this, you get cube 3 capital R square minus small r square. So if you draw the graph, of field, potential versus R, it will be like this. This is a rectangular hyperbola and this is a parabola, and this parabola becomes flat here. Why it becomes flat here? Because at the center, that E is equal to minus dV dr here. Yeah, it's a single variable function R, na? Radially symmetric field. So minus dv dr. So as here field is equal to 0, so dv dr equal to 0. That means it should be flat. And this part of the curve is parabola. While the other part of the curve, this part is a rectangular hyperbola. Though these concentric shells will uh, do in much details. I mean the concentric conducting shells will do in much details when we learn about Gauss's theorem and properties of conductors. This was due to a solid sphere, right? This was due to a solid sphere, and due to a shell, what was it? Due to concentric shell, uh, due to a single shell, it was this, right? It becomes straight, becomes flat, same potential. And here see potential increasing. Why? Because more potential, high to less potential means that is the direction of the field.